Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
I'm often asked, what are the Philip Emeagwali equations? Or how were the Philip Emeagwali equations derived? The Philip Emeagwali equations are a system of coupled, nonlinear, time-dependent, and three-dimensional partial differential equations that are symbolic restatements in calculus of multi-phased fluids flowing across a porous medium. The Philip Emeagwali equations encoded into calculus the second law of motion of physics. The Philip Emeagwali equations model the three-phase, three-dimensional flows of crude oil, natural gas, and injected water that are flowing 1 mile deep and flowing across an oil field that is the size of a town. I have been presenting the Philip Emeagwali equations to research mathematicians and doing so since the early 1980s. The Philip Emeagwali equations were the cover story of the June 1990 issue of the Siam News. The Siam News is the premier publication for mathematicians. The Siam News is the flagship publication of the Society for Industrial and Applied Mathematics. The Siam News presents new mathematical knowledge as written by research mathematicians for research mathematicians. I also presented the Philip Emeagwali equations at invited lectures that I delivered to research mathematicians in the United States. I delivered an invited lecture on my contributions to mathematics, and I delivered that lecture to the largest international congress of mathematicians called ICM 91. That congress is the Olympics of the world of mathematics and is held once every 4 years. My ICM 91 lecture was at 11 in the morning of Monday, July 8, 1991, in the Dover Room of the Washington Sheraton Hotel in Washington, in the District of Columbia, United States. The complete mathematical description of the invention of the Philip Emeagwali equations is posted at emeagwali.com and shared at the YouTube channel of Philip Emeagwali. In summary, the Philip Emeagwali equations is akin in mathematical structure to the iconic Navier-Stokes equations that were used to design jet aircrafts and used to model the flow of blood flowing across veins and arteries. Due to its importance, the Navier-Stokes equations were used to define one of the 7 millennium problems of mathematics. The system of Navier-Stokes equations owes itself to the oceans, wind, and fire, just like the system of Philip Emeagwali equations owes itself to the injected water, crude oil, and natural gas that flows 1 mile deep and flows inside an oil field that is the size of a town. The differential equation plays a central role in sub-disciplines of mathematics, such as complex analysis, Lie algebra, and probability theory. My discovery of practical parallel processing can be extended to all boundary value problems of calculus that are governed by partial differential equations, such as Maxwell's equations of electrodynamics, diffusion equation of heat and mass transfer, beam and plate equations of solid mechanics, lubrication theory of fluid mechanics, Huxley equations of neurobiology, Fisher's and reaction diffusion equations of genetics and population dynamics, and the Black-Scholes equation of financial engineering. For these partial differential equations, the time scales for discretizing and solving them range from 1/1,000,000th of a second to 1,000 years, and the length scales for solving them range from the subatomic to the astronomical. The various formulations of the partial differential equations governing the flows of fluids were almost independently derived by Claude Louis Navier, Simeon Denis Pouzin, Barre de Saint-Venant, and George Stokes. Those partial differential equations were derived between 1827 and 1845. The Philip Emeagwali equations were my independent derivations of new partial differential equations that I formulated when I was a research mathematician of the early 1980s and in College Park, Maryland, United States. The Philip Emeagwali equations were the governing equations that encoded the time-dependent and three-dimensional subterranean flows, motions, of crude oil, injected water, and natural gas that flow 1 mile deep and across an oil field and towards production oil wells. The mathematical difference between the Navier-Stokes equations as written in the Millennium Problem of Mathematics and the Philip Emeagwali equations is that the latter govern the three-dimensional, three-phase fluids flowing across a porous medium that is 1 mile deep and that is the size of a town. Please allow me a couple of minutes to speak only to the mathematicians in this audience. In most fluid dynamics textbooks, the Navier-Stokes equations are written in compact vector form as rho, the fluid density, times the sum of the partial of v, the fluid velocity in vector with respect to the partial of t, the independent variable time. That is the change in velocity with respect to time that is called the temporal acceleration, plus the product of the fluid velocity in vector and nabla or upside down delta and the gradient operator v, the fluid velocity in vector, that is the convective acceleration, is equal to minus nabla p, the fluid pressure term, that is the fluid flows in the direction of the largest change in pressure, plus the product of nabla and capital T, where T is the stress tensor for viscous fluids, plus F, the body forces such as wind, gravity, and electromagnetism. I stated a vector equation for each of my three phases, namely crude oil, injected water, and natural gas. That is equivalent to 9 scalar equations. My unknowns were the velocity and the pressure. In 3 spatial dimensions, I have 3 equations and 4 unknowns, namely the pressure and the 3 scalar velocities. For that reason, I introduced a system of supplementary partial differential equations. Those extra partial differential equations encode the law of conservation of mass for the crude oil, natural gas, and injected water. Those continuity equations are the products of nabla, or the gradient operator, and V, the fluid velocity in vector, equals 0.
Insightful and brilliant lecture.